Alright, so we looked at, we stopped in the last lecture by observing that there are ways to quantify the conduction process. So we are going to go deep into that today and look at what are the ways to quantify and look at certain examples and certain types where we can look at the quantification process and try to understand what is the temperature distribution. So we stopped by observing that we need to find the temperature distribution So in order to quantify the system, we need to find the temperature distribution. So if we know the distribution, obviously we will be able to find out the gradient, that is the dt by dx, the temperature gradient at any location in the system. And if we know that, we know the transfer rate. We know the flux and we multiply by the transport area, we will know the heat transfer rate. Okay. So we need to write energy balance, so which means that we need to write a energy balance. Okay, so let us take a general differential element. So x, y, z. Okay. Qz, and what comes out is Qz plus delta z, Qx, x, Qy, dy. So those are the rate at which heat is entering different surfaces of the element, and we could add a, we can say that Q dot is the rate of heat generation per unit volume. So in principle, something could be happening inside. For example, there could be electrical heating which leads to generation of heat inside the system that you are considering. So Q dot could be the volumetric rate of heat generation, that is the amount of heat that is generated per unit volume of that system. So the volume of this small element V is nothing but delta x multiplied by delta y multiplied by delta z. Okay. So we know that. So let us write a simple balance. So the general thumb rule, okay, for writing any balance, whether it is heat or mass balance, is that we say input to that element minus output plus generation term, that should be equal to the amount that is accumulated. That will be accumulation. So you could call this I, you could call this O, you could call this G, and you could call this A. Okay. So this is the mantra of all the balances that you would be writing in this course and perhaps in many other courses till you finish your BTech. And in fact, this is the mantra in almost all the balances that you would write in any engineering discipline, irrespective of whether it is chemical, mechanical, etc. So this is the general mantra, and we won't go dwell more into this. So we will use this mantra here today, and then we are going to write a general balance for conservation of energy for this system, and we will use that balance and try to simplify for different kinds of systems that we are going to look into in the future. Alright, so what is the input to the system? The amount of heat that is input is Qx, right, plus Qy plus Qz. So that's the total amount of heat rate at which heat is being input to that system that we are considering, and what leaves is Qx plus dx, Qy plus dy minus Qy Z plus dz. That is the amount that is leaving the element that we have considered, plus whatever is being generated. So you have to be very careful. So when you have a heat loss term, when you have a sink term or heat loss term, then you have to use a negative sign. So you have to be very careful about the sign convention that you use for any balance that you generally make. Okay. So that could be Q dot. So this is defined as rate of heat generation per unit volume. So therefore you have to multiply by the volume of the system that you are considering, and that is equal to the accumulation, which is given by rho Cp, which is the density of the material that you are using, multiplied by the specific heat capacity into the temperature gradient with respect to time, multiplied by the volume. So that is the heat balance. So it is very simple. Input, what goes out, you subtract that, and whatever is generated you add to the system, that should be equal to whatever is being accumulated. So this term tells you what is the amount of heat that is actually being stored, what is the amount of energy that is being stored by the system because of the heat transport process. So this tells you what is the capacity of the system that you are looking at, and Cp is the parameter, intrinsic parameter, which quantifies that capability of that system as to how much heat that it can store. Okay. So now we can simply divide these equations by the volume, and so it will be, so are the units matching here? Cp is per unit volume, okay. Are the units matching? Look at the units. I want you to pay attention to the units. Is the units matching for all the terms here? So you have to convince yourself when you are actually in the class, everything that is happening is right. Is it right? No. What is wrong? Which one? Where? This one here? Yeah. Why is that a problem here? But it's already taken, right? Watts per meter cube is the unit of Q dot. So you multiply by volume, it becomes watts. What is the units of Qx? It's watts. It is watts. It's not flux, it's transfer rate. It's rate of heat transfer. Keep in mind the convention that we used, okay? You should always remember this. When I say Q, it is rate. When I say Q single prime, it's rate per unit distance. And when I say Q double prime, it's the flux, that is the rate of heat transfer per transport area, okay? Alright, so now I divide the equation by, so Qx plus dx divided by delta x into 1 by, excuse me, joule per kilogram Kelvin, and rho is kg per meter cube. So that is why you have to multiply by volume, okay, plus Qy minus Qy plus delta y divided by into 1 by okay. So moment we formulate it in this form, all I have done is I have just divided the equation by the volume, and I have just collected the terms which corresponds to x, y and z together. So the important thing to observe here is that this delta y delta z, which appears as a coefficient for the rate terms in x direction, that is nothing but the area of heat transport in the x direction. So that tells you what is the cross sectional area at which the heat transport is occurring in the x direction. That is basically this plane here. You see this plane here, delta x. It is the plane in the z and the y direction. Similarly, delta x delta z is the cross sectional area of heat transport in the y direction, and similarly for the z direction. Okay, is that clear to everyone? Okay, alright. So we can rewrite this as, so when I say that limit delta x goes to 0, delta y goes to 0, and delta z goes to 0, so we can write this as dq by dx 1 by delta y delta z plus, it's a minus sign, minus dq by dy delta z dz dot. Okay. So with this, can I get the temperature distribution? Yes or no? Can I get the temperature distribution with this? So if we know what, yes, if some constitutive relationship, so we don't know what Q is, so if there is a constitutive relationship, if you have not heard this word, it's called constitutive relationship. If we know the constitutive relationship between Q and temperature, we are done. So if we know the constitutive relationship between the transfer rate and the temperature, then we are done. We have completely described the temperature distribution. We don't know the distribution because we have to solve the equations, but we have described it completely. Okay, and this is what is given by Fourier's law that we saw in the last lecture. So Q is given by the area of heat transport in whichever direction you are considering. Supposing if it is x, it's the area of heat transport in x direction multiplied by the corresponding flux in the x direction, right? And so this is given by minus k. So supposing I assume that the system is isotropic, so if I assume that it's a isotropic system, there is no reason that you should not assume it, but let's say that for simplicity we assume that it's a isotropic system, although all the framework does not change whether the system is isotropic or non-isotropic, but let's say for simplistic purposes we assume that it's isotropic. So there will be k into, what's the area of heat transport in x direction? Delta y delta z. So we observe that, so that's the coefficient that comes out in your energy balance into dt by dx. So that's the representation of Fourier's law in the x direction. Similarly, we can write for y minus k y, and qz is az So we can substitute all this into the model equation now. So this is what is called the energy balance or model equation. That's what is called the model equation. So we can substitute these fluxes from Fourier's law into the model equation. d by dx into k into delta y delta z plus d by dy k into plus q dot equal to rho Cp into dou T by, okay. So supposing if the area does not change with the cross sectional area is constant, supposing for a system in case of Cartesian coordinates, you will see that the cross sectional area of heat transport remains constant. So if we assume that for a system where area of heat transport is constant, we will see in future, we will see few examples of where area is not constant and how these model equations will change. But let us say to start with, we assume that the area of heat transfer is constant, which means we can pull out delta x, delta y, etc. from the derivatives inside, and so this will simply become k into d square t by dx square plus d square t by dy square plus d square t by dz square plus q dot equal to rho Cp dou T. So this is the energy balance. Okay. What is this term in the bracket called as classically? It's called the Laplacian. So one could rewrite this expression as del square T plus q dot divided by k equal to rho Cp divided by k into, so it's just a cute way of writing the energy balance. What is this term? Does anyone know? Yeah? Prandtl's number is non-dimensional. It's a dimensionless number. This has a dimension. Rho is kg per meter cube, Cp is joule per kilogram Kelvin, and K is watt per meter Kelvin. So what are the units of this quantity? So the units are, it's K by rho Cp, the unit is meter square per second. Yes. Because in principle the system need not be isotropic, right? So if it is not isotropic, then you would expect that this K's will be different, and of course the gradients can obviously be different. So therefore you have to distinguish the fluxes in all three directions and the transfer rate in all three directions. It's, it should be Qx, Qy. Sorry, thanks for pointing that out. Please correct your notes. It should be Qx, Qy, it's a typo. So Qx, Qy and Qz are the transfer rates in the corresponding directions, okay. Alright, so the units of this K by rho Cp is meter square per second. Can you guess what it is, what this quantity is from the units? It's diffusivity. So it's called, so this quantity is called thermal diffusivity. Thermal diffusivity. So what it signifies is K is the thermal conductivity and rho Cp is the capacity of the system, right? So this is the ratio between the ability of the system to conduct heat versus its ability to store the energy, right? So rho Cp, remember what I told you a few moments ago, rho Cp is characterizes, it's in the intrinsic property that quantifies the ability of the system to store heat within itself, store energy within itself, and K is the intrinsic property of the system which characterizes the ability of the system to transfer heat from one location to the other via conduction. So this is the ratio between the ability of the system to conduct heat versus the ability of the system to store heat within itself, and that is what is called thermal diffusion. Yes. So this is the, so what happens, so there are there are two processes which are occurring simultaneously. One is the energy is being transferred because there is collisions between the electrons, or there is lattice waves which is happening, and so there is transfer of heat from one electron or one molecule to the other molecule. Now, when the temperature is increased, the energy state of that molecule also is going to be increased, right? So, the rho Cp, it signifies the ability of the molecules to store heat because of higher temperature, and the interaction between them is the one which is going to signify the ability to transfer the heat. So, this ratio is basically the thermal diffusion, and the reason why this ratio is thermal diffusion is, supposing if the material has a very high capability to store heat, then the amount of heat that it can transfer because of the interaction is going to be very small. So, it is a competition between the ability to transfer heat because of the interaction versus the ability of that system to store the heat in the same location, the same molecule, and that is why it is called diffusion. In fact, that is the definition of diffusion. Any other questions? Okay. So, is it enough to just write the balance? Have we completely described? Can we solve this equation now? Is it possible to solve? What do you need? This is a partial differential equation. What makes a PDE complete? You need boundary conditions, right? So, let us now discuss for the next few moments as to what are the different types of boundary conditions, what are the general classes of boundary conditions, okay? Okay. So, there are three basic classes of boundary condition or three types of boundary condition. One is the constant temperature boundary condition, constant temperature boundary condition. So, for example, if you take a system, okay, so let us say this is x equal to 0, okay, one possible boundary condition is you could fix the temperature of that particular boundary, okay. So, you can say that the temperature is fixed at some constant. So, typically I use subscript S for surface, so it could be surface temperature. So, we can say that the temperature at x equal to 0 is maintained at a certain constant temperature Ts, okay. So, that is one type of boundary condition. So, there are several examples of this. So, supposing if you want to, let us say you have water geyser, right. So, we have geysers at our residence in our bathroom where we get hot water, right. So, the temperature of the surface, so you see there will be a heating coil. So, the way the geyser works is there is a heating coil which is electrically heated, and there is a thermostat which maintains a certain temperature of the heating coil. So, note that it is not the temperature of the water that it maintains, it is actually the temperature of the heating coil that it maintains. So, if you are trying to write a model of this system to find the temperature distribution of water, then one of the boundaries to which the coil is exposed to which the water is exposed to the coil will actually be maintained at a certain constant temperature. So, it is a constant boundary condition, constant temperature boundary condition is what you should use at that time. Okay. Another type of boundary condition is called the constant flux boundary condition. Okay. So, this is the second type. There are two different subtypes in this case. One is zero flux. So, note that 0 is also a constant. So, zero flux and then non-zero flux, non-zero constant flux. Okay. So, the way to look at it is, supposing if you have a zero flux, okay, at x equal to 0, if you have zero flux, then you would expect that so if I look at the temperature profile inside near x equal to 0, because the flux is 0 at that location, you will see that the temperature is going to be flat, it is going to be parallel to the x axis. So, we could describe this by an expression. we can say dt by dx at x equal to 0. So we can describe this boundary condition by the following expression: dt by dx at x equal to 0 equal to 0. So that's the no flux boundary condition or zero flux boundary condition. And then you can have a constant flux where you say dt by dx at x equal to 0 is some constant. Oh, there should be a k. So the flux is k into dt by dx and with a minus sign. So keep in mind that you should not forget the minus sign. Why is there a minus sign? Because the energy transfer is in the negative temperature gradient. So minus k dt by dx at x equal to 0 is equal to constant flux. Okay. And then the third type of boundary condition is the variable flux boundary condition, or it's sometimes simply called as flux boundary condition. Okay. But really it's variable flux boundary condition, just to distinguish between the second type. Okay. And so that is simply given by minus k dt by dx at x equal to 0 equal to some flux which is a function of the local temperature. Okay. So how can we define this flux? Is there a way to quantify this variable flux? Is there a way to quantify this flux? Remember that for conduction we said the quantification is done by Fourier's law. What about this? Any suggestions? I'll give you a hint. It's also called as convective boundary condition or convection boundary condition.